Yeah, we've got a new model that can interact with the world through audio, vision, and text.
When GPT-4o or Omni was released, there was so much excitement about the super cool voice and visual recognition and generation that we overlooked an important aspect of it that I will be discussing today based on this paper by several Stanford University researchers, including Andrew Ng. But before that, let's take a quick look at some of its multimodal and amazing features, such as live translation.
We'd like you to act as our translator for us.
Sure, I can do that. Let's get this translation train rolling.
Real-time recognition of moving objects and animals.
Little thing.
Yeah.
Look at you enjoy.
This is one of his favorite things to do.
Real-time visual recognition of historical sites to help people with visual impairment.
Is the king in residence at the moment?
Yes, it looks like the king is in residence right now.
And two GPT-4os role-switching between customer and customer service.
Ring, ring.
Hey, Joe. This is Jamie from Acme Telco. How can I help you out today? Hi there. I'm calling on behalf of Joe, who recently received a new iPhone from Acme Telco.
Among many others. In all these examples, GPT-4o was communicating with a close enough audio source and recognizing ordinary objects in close proximity or famous landmarks that are prevalent in most training datasets. But what if you're doing research in a specialized field, let's say medicine, and have to sort, classify, and visually recognize issues in the type of data that are not very prevalent, and you don't have access to a fine-tuned version of GPT-4o? Well, this paper on many-shot in-context learning in multimodal foundation models has explored this exact issue and came up with pretty interesting findings. Its opening sentences read, "Large language models are well known to be effective at few-shot in-context learning or ICL. Recent advancements in multimodal foundation models have enabled unprecedentedly long context windows, presenting an opportunity to explore their capability to perform ICL with many more demonstrating examples." If you are new to this concept, in-context learning is providing the LLM with some contextual examples, also called shots, before testing the model on the actual question or query. Here's a demonstration of the concept by way of providing in-context images, whereby the model has to decide whether this image on the right is a forest, golf course, or freeway. As you see, in zero-shot, no example of these are provided. In few-shot ICL, only one or a few examples are given. In many-shot ICL, a large number of examples are provided, whereas the most advanced setting or batched many-shot ICL can perform multiple queries using multiple references or examples. Up until now, in-context learning enabled LLMs to learn from few shots without any updates to model parameters, and therefore improved specialization to new tasks without any further model training. Recently, experiments have been conducted on large multimodal models, or LMMs, for the effects of in-context learning, especially out-of-domain or out-of-distribution tasks. The issue so far has been the limited context window of most LLMs and LMMs, which constrained them to only few-shot learning. But more recent multimodal models are capable of accepting longer context windows. For example, GPT-4o enables 128,000 tokens, and Gemini 1.5 Pro can take an astonishing 1 million tokens, which prompted these guys to see the effect of ICL on model performance without any additional model training or parameter updating. So they benchmarked these two LMMs' performances on 10 image datasets such as medical imagery, natural imagery, remote sensing, and satellite imagery, and found that both models' response accuracy is tremendously improved with many-shot ICL. Here you can see how GPT-4o improves its accuracy from zero-shot to many-shot on the satellite imagery dataset of Eurostat for land use classification, and how Gemini Pro outperforms in animal species recognition on camera images. On the UC Merced satellite images, both models reached an astonishing 98.57%, and on medical imagery they are even better than human-level accuracy. That's quite something. Moving forward, this begs the question of, do we need to constantly fine-tune old models now that we have these long context sizes and such proven high performances even with multimodality? Couldn't in-context learning be just the next big thing, as everyone can carry out these on the fly, incorporating them in carefully designed prompt formats? Feel free to pause the video to read these sample prompts from the paper on image classification for many-shot and batching ICL. As you can see, there are some advantages of incorporating ICL into AI-based projects. Perhaps the main advantage is providing a training-free method whereby you do not need to fine-tune the models with your specific data and change the model parameters. The ICL is usually done with natural language prompts, and the whole idea is very similar to how humans learn by analogy. This taxonomy of ICL depicted by Vincent Tu also shows more sophisticated versions of in-context learning, for example, supervised and self-supervised warm-up stages, as well as prompt formatting and selecting the scoring function, along with the studies that have experimented with this. To have better results with ICL, we ideally want to increase the probability of the output based on the class labels that maximizes the scoring function. This scoring function for any of the LLMs basically estimates the likelihood of each output given the input. A word of caution is how ICL can be sensitive to the type and number of examples in the prompt, as well as the prompt format of the query itself. This is because we are still in the early stages of ICL research, and better scoring functions are needed to moderate sensitivity and bias. All in all, given these significantly positive results, do you think the near future will witness more informal methods such as on-the-fly in-context learning for adapting LLMs to specific tasks than more traditional methods such as gradient-based training, fine-tuning, and changing the model parameters?